When we run least squares regression, we get estimates of the parameters for our model. But if the data contain randomness, if there's any stochastic part to the process, it's not going to be the same every time we run the process, so we shouldn't expect the parameter estimates to be the same every time. In fact, the parameter estimates aren't going to be the exact true parameters. They're going to be estimates. They'll in fact be random variables. There will be randomness in our parameter estimates because there's randomness in our data. I'd like to demonstrate this somewhat vividly. I'm going to generate some random numbers, 101 of them, to make a little time series, and then I'm going to do linear regression on that time series and estimate the slope and the intercept. And I'm going to see whether it comes out to be exactly 0 because I'm going to set things up so that I know ahead of time there's no trend. The true intercept and the true slope are exactly 0 in these cases, but the estimates we get from linear regression should be ever so slightly different from 0 because of the randomness in the data. And I'm not going to just do that once. I'm going to do it 1,000 times just to see what I get. It's kind of interesting to watch, actually. Fortunately, the computer does it quite rapidly, so we can watch it happen and not have to wait too long until we've done 1,000 simulations and made 1,000 estimates of the intercept and the slope when analyzing random noise. Voila, we've got it. What about the intercepts? Did they come out to be about 0 as they should? Well, they're pretty near to 0. In fact, they're clustered around 0. They are fluctuating a lot, so there appears to be randomness. Then again, we kind of expected that. But we also expect that it'll be random near 0, and it certainly appears to be random near 0. As a matter of fact, it seems like it's following perhaps the normal distribution. We can test that idea by doing what's called a quantile-quantile plot. If something's following the normal distribution, then a normal quantile-quantile plot will roughly follow a straight line, and it does. That's pretty good visual evidence, but it's really nice to have a rigorous statistical test. Let's do a test for the normal distribution called the Shapiro-Wilk test. With a p-value of 0.8, there is absolutely no evidence of any departure from the normal distribution. So the intercept parameters came out pretty darn close to 0 and seem to be following the normal distribution. What about the slopes? The slopes also tend to be pretty darn close to 0, as we expected, because that's the true slope. And again, they fluctuate around apparently randomly because we expect them to be random variables which are influenced by the randomness in the data. If we look at a histogram, we see that, yeah, it seems to be clustered around 0. Maybe it's following the normal distribution too. If we do a quantile-quantile plot, that's pretty close to a straight line also. Strong evidence visually that it's following the normal distribution. And if we run the Shapiro-Wilk test, we get a p-value of 0.16. So again, there's really no evidence of any departure of a significant nature from the normal distribution. The important lesson is that the parameters may have some particular value, we don't know what it is. When we use data to estimate those parameters, if the data have randomness, our estimates will include randomness too. Our estimates are random variables, so we shouldn't expect them to be exactly correct. It would be nice, however, if we could quantify just how uncertain they actually are.